Hello everyone. Welcome to the new Trent Seaman Center for Health Education at Duke University School of Medicine. I'm really happy to share this short tour of some of my favorite places in the human brain with you all. And this is a bit of an insider's look at the human brain. I'm going to share some of my biases with you about what intrigues me about the brain. And since it's something of an inside story, I thought, I should probably go to some inside place to film this. So we are in the specimen prep room for the Duke University School of Medicine for the laboratory courses that we teach with human brain specimens. And as you can see behind me, we have quite a number of human brain specimens in our collection. This is the place where we store, where we curate the specimens, and where we prepare them for our teaching. So in front of some of my favorite specimens, I'm just pulling one out and give you a chance to see up close and personal, as it were, some of the parts of the brain that especially intrigue me. So here's a brain from our collection, and I hope you can see it well. So we're looking at the anterior aspect of the brain, the right hemisphere, the posterior aspect, the left hemisphere, the dorsal surface, and I'm sure you can see the mid-sagittal plane there, where we have our longitudinal fissure separating the right hemisphere from the left hemisphere. And then on the ventral surface, I think a really nice demonstration of the ventral surface of the human brain, including the brain stem, the blood supply that enters the brain from its inferior surface, and the cranial nerves. Well, some of my favorite places in the brain. I would have to begin with the central sulcus. The central sulcus in the right hemisphere is this sulcus that we can see working its way from the dorsal midline in the superior longitudinal fissure all the way out to the lateral fissure. And I want you to notice the shape of this central sulcus, because I'm going to show you the left hemisphere, and you'll see that even in the same brain, the corresponding regions that you might think would reflect the symmetries of the body really can be quite different. So there's the right central sulcus, and now here's the left central sulcus. One feature that I think is quite different is that in the right side, there's a very distinct omega shape in the middle of the central sulcus, whereas in the left hemisphere, the central sulcus is much more straight. So here's the left side, and here's the right side. And my fingertip is right at that omega shape that I referred to. Well, that omega shape is roughly where the hand is represented in the somatic motor and somatic sensory cortex, with the somatic motor cortex being on the frontal lobe side and the somatic sensory cortex being on the postcentral side. I spent quite a few years working with a wonderful mentor, scientist and friend, Dr. Dale Purvis, and together we explored asymmetries of this region of the human brain, comparing the right hemisphere with the left hemisphere. And we were particularly interested in the notion of human-handedness and whether there was an asymmetry of the brain that related to human-handedness. Well, our studies were followed up by others who pursued this question, and it does indeed seem as though in the cerebral cortex there's more circuitry devoted to the preferred hand than the non-preferred hand, which raises some interesting questions, such as, is brain like muscle? Is bigger better? Does more skill necessarily mean more circuitry? Or does better skill simply mean better circuitry, not necessarily more circuitry? Well, these are fascinating questions that have been with us as long as people have been interested in studying the human brain. And that journey led me to explore this region of the human brain once upon a time ago. Well, more recently, my interest has been in the back of the brain. Here we have the occipital lobe, and the occipital lobe is home to our primary visual cortex and a series of associational visual areas that elaborate more and more abstract features of vision. I can't show you the primary visual cortex in this specimen because we'd have to look on the mid-sagittal plane, but I can show you roughly how visual information is processed in the occipital lobe. Signals first reach the medial portion of the cortex that forms the calcarine sulcus. That's our primary visual cortex. And from there, information generally is passed through a series of interconnected cortical areas, some of which tend to stream down the inferior aspect of the temporal lobe. We call that the temporal processing stream. And these areas on the ventral temporal lobe are especially concerned with recognizing the objects, the places, and even the faces that we encounter in our daily lives. For example, your face, or the face of your family, or the face of a loved one, is encoded in the areas that we find on the inferior surface of the temporal lobe. And unfortunately, there are people who have had strokes or other kinds of brain injuries affecting this part of the brain. And as a consequence, some of these folks lack the ability to recognize familiar faces. It's not that they're blind, it's that they fail to understand the significance of the visual stimuli that comprise a human face. Well, visual information is also sent along a more dorsal trajectory into regions of the parietal lobe and regions around the junction of the posterior temporal lobe, the occipital lobe, and the parietal lobe just above. This region of the occipito-temporal parietal junction is where we find some interesting areas that are especially concerned with motion processing. In fact, there's a region probably right about here in the human brain that corresponds with an area well studied in primate animal models called area MT, for middle temporal visual area. And this area is famous in neuroscience circles for being enriched in cells that have very sharp and precise preferences for direction of motion. This seems to be a region in the visual parts of the brain where our understanding of motion, or as our chair in neurobiology here at Duke likes to say, where we build our notion of motion. That would be our chair, Dr. Stephen Lisberger, who gives wonderful talks on that subject. Well, the visual cortex is a part of the brain that I studied in my career after leaving the central region and exploring questions related to human-handedness. I moved on to animal models and studied aspects of vision and the organization of circuits in the visual cortex that pertain to understanding the fundamental aspects of visual perception, such as the orientation of the shapes and the lines and the angles that we see in our visual world, and the patterns of motion that either we generate as we move through the environment or objects in the environment that are in motion generate as they pass across our retinas. Well, that's a bit of personal history. Let me move on and just highlight some areas of the brain that are really great interest to neuroscientists today and over the years, and some areas that are especially hot in today's world of neuroscience. Well, we're looking at the left hemisphere, so I should highlight some of the language areas that seem to be especially lateralized in the human brain. One that you probably know about is called Broca's area. Broca's area is found right about here, which is in the posterior portion of the inferior frontal gyrus. So Broca's area is a region that helps us produce speech, whether it be vocal speech or written speech. And although this is not well studied, probably written speech using our digital media that we use so often now to express ourselves in words. There are other areas that are specialized for different aspects of language, such as understanding language, be it in spoken speech or in written form. And those areas are distributed in the lateral superior temporal lobe, although most likely there is a broad network of brain structures that are distributed around the lateral temporal lobe and perhaps even into the inferior parietal lobule that are important for understanding speech. Classically, we call this Wernicke's area, but now I think we understand that it's not a single area corresponding to a cytoarchitectonic region, for example, but it's probably a network with multiple nodes that are encoding various dimensions of language for the purpose of understanding language. I know many of you listening to me are bilingual or multilingual, and for you, you very well may have different nodes that are important for understanding your various languages. And for those of you who utilize American Sign Language, yes, you probably have a node somewhere in here that encodes your visual understanding of language as expressed in the motions of the hands and the face. Well, let's turn over to the right hemisphere. Indeed, we've got corresponding structures in the right hemisphere in the position of the posterior part of the inferior frontal gyrus and in the superior part of the lateral temporal lobe. We conventionally don't call these areas Broca's areas and Wernicke's areas because if there were injuries here or if these areas were dysfunctional, there would still be speech and understanding of speech. However, something would be lost. Probably what would be lost is the ability to imbue speech with emotional tone and the ability to understand tone. Well, here in the United States of America, it happens to be Valentine's Day. And while we're thinking about making speech in the right hemisphere, I can't help but to think of the stories in the literature of marriages that have been broken over damage to the right hemisphere, specifically in the region of Broca's area. Imagine this: one spouse declares to another, "You don't love me anymore." Of course I love you. Why don't you believe me that I love you? Well, the idea here, and I'm not replicating this very well, but one spouse no longer believes the words by themselves because the other, who perhaps has had a brain injury to the right inferior frontal gyrus, can no longer imbue speech with passion, with the emotion that is the life force of our human relations. So although right hemispheric lesions are ineloquent, as sometimes we hear the neurosurgeons say, they can be nevertheless devastating to the human condition. Well, lastly, I want to show you a fascinating part of the brain that we'll come to near the end of medical neuroscience. And it's this part of the frontal lobe that sits directly above the orbits of the eyes. This is called the orbital cortex, and it's a part of the brain that was damaged in a famous case in the medical literature from the 19th century. I'm sure many of you know about this case. It's the case of Phineas Gage, who almost unbelievably survived a horrific injury where about a 13-pound, nearly meter-long iron rod was blasted through his skull, producing significant damage to the orbital and medial part of the frontal lobe in a region that we call the prefrontal cortex. Well, much has been written, much has been said over the years about the change in Phineas Gage's personality, his demeanor, his social mores. The fact is, we just don't know much of what is truthful about Mr. Gage following his injury. But there is a fascinating literature that's growing, examining people that are with us now who've had injuries to this part of the brain. And what we're learning about them is that their decision-making faculty has been impaired, especially decisions that pertain to their personal self and decisions that affect what they themselves are invested in emotionally and socially. And so this is a part of the brain that's critical for the integration of emotions and cognition in such a manner that it allows us to predict the future. That is, to weigh the consequences of our decisions and to act accordingly. So a fascinating part of the human brain that you'll be hearing some from me about later in the course, and continues to attract great interest from neuroscientists around the world who are trying to understand the networks and the circuitry and the physiology of this part of the human brain. Well, lastly, I want to show you the brainstem. This is really a wonderfully complex part of the human brain. Many neuroscientists are interested in this part of the brain. Sadly, many more are not. But for those of you interested in pursuing a career in healthcare, the brainstem is a critical part of the human brain, not only for its functions, but for what understanding the brainstem can tell you about your patients while you're proceeding with your interviews, your histories, and your physical examination. We have a number of beautiful cranial nerves that are visible here. I doubt you can see very many. In this perspective, it's really not my intention to show you those nerves here. We have an entire tutorial devoted to the cranial nerves, so I'd refer you to that. Nevertheless, we're going to try a bit of manual brain zoom to see if you can track the cranial nerves and see it as closely as possible. Okay, well, I'm nearly done showing you some of my favorite places in the human brain. Let me just conclude by quickly going over the 4 lobes of the cerebral hemispheres, which I hope will soon be very familiar to you as you view our videos of actual brains, as well as refer to our tutorials with illustrations and pictures. And for those of you who've purchased the textbook, you can look in the appendix and read about the anatomical organization of the cerebral hemispheres there. Okay, so looking at the right hemisphere, we have the frontal lobe to the anterior side, the occipital lobe to the posterior side, and in between the frontal and the occipital lobe is the parietal lobe in the superior aspect of the hemisphere and the temporal lobe in the inferior aspect of the hemisphere. The dividing line between the frontal lobe and the parietal lobe is the central sulcus. My index finger overlies the precentral gyrus, my middle finger the postcentral gyrus, and the space between my fingers representing the central sulcus. So the central sulcus is the division between the frontal lobe and the parietal lobe. The division between the parietal lobe on the occipital lobe depends upon what we can see from the mid-sagittal plane. Right about at the position of my finger is the parieto-occipital sulcus, which marks one point of demarcation between the parietal lobe and the occipital lobe. The other is a feature of the inferior aspect of the hemisphere called the preoccipital notch, which is attributable to a flap of dura that sits between the cerebellum and the occipital lobe called the tentorium. So an imaginary line between the parieto-occipital sulcus and that preoccipital notch is what divides the parietal lobe from the occipital lobe, and then the temporal lobe in front of the occipital lobe. So our temporal lobe then extends forward. Well, thanks for spending a few minutes behind the scenes with me in our specimen prep room in our Trent Seaman Center for Health Education. I hope you enjoyed this. I know I did. And believe it or not, I've got to teach a class in just a few minutes, so I'll sign off for now. Thanks for being with me, and I'll see you next time.